Hello friends. So in today's question, the arrangement shown in the figure, the rod of mass small m held by two smooth walls remains always perpendicular to the surface of the wedge of mass capital M. Assuming all surfaces are frictionless, find the acceleration of a rod and that of the wedge. So this is the wedge and this is a movable mass rod and these two are the fixed walls. What we do, let us first of all draw a line parallel. So obviously this angle we are going to get, it will be alpha, and this angle we are going to get 90 minus alpha. Okay, so let us extend this one. So we are going to get this angle also 90 minus alpha. Okay. And see that it moves by E2 acceleration capital M towards this direction, and the mass, or we can say rod, is moving with the acceleration F1 in this direction. So we have two normal reactions. First will be applied by wedge on the rod, and let us suppose it goes in this direction, and another one will be this direction. Okay, and we're also going to have a mass mg in the downward direction. So these are the few forces, the mg, normal reaction, and angles and acceleration associated with m mass and capital M. Okay, so we say that mass m moves with acceleration E1 mass small m moves with acceleration E2 I think that will be sufficient. Okay, so let us consider first of all the mass rod M. Okay, so we can say that for rod of mass small m, we are going to have mg force in the downward direction like this. Now it can be divided into two components. Okay, so we are going to have this one as mg sine of 90 minus alpha, and this will be mg cos of 90 minus alpha. So we can write in an equation which states that mg sine of 90 minus alpha minus n will be equal to mass into acceleration. Okay, and this equation we can write this as writing mg cos alpha minus n is equal to ma. Let this be our first equation. Similarly, for wedge, mass capital M can divide our normal. This is the normal, and it can be divided into two components like this. So we have this as n cos of 90 minus alpha, and this will be n sine of 90 minus alpha. Therefore, you can say that n cos of 90 minus alpha will be equal to m e2, and and this as n sin alpha is equal to m a2. Let this be question number 2. Now we are going to find out the constraint relationship between A1 and A2. Okay. Constraint relation between acceleration A1 and A2. The important thing is there, let this point of contact is given as P. Okay, so as rod of mass m should be always in contact with the wedge of mass capital M. Okay, so under this condition, the velocity of, you can say velocity of small m should be always equal to velocity of capital M, and we already know velocity is, we have a relationship between velocity and acceleration, so we can also say that the acceleration should be also equal. The acceleration should also be equal. And let us consider this point number 1. This considering as point number 1. In the point number 2, it states that point number 2, the acceleration A1 and A2 are in different direction. Okay, acceleration A1 and A2 are in different direction. Okay, you can clearly see that our A1 is in this direction, whereas the A2 is in this direction. Therefore, we can resolve A2 into the two components, and one of the component will be aligning along with the direction of A1. Okay, can divide, therefore dividing A2 into two components such that we get A1 is equal to A2 sin of alpha, and this is our equation number 3. Now, using these three equations, we are going to find out the acceleration of wedge as well as the rod. So we have three equations. Let us write it one by one again here. First is mg cos of alpha minus n is equal to m A1. Second equation, we have that n sin alpha is equal to m A2, and the third equation, which we already derived here, is A1 is A2 sin alpha. Okay. So first of all, from this equation, we find out what is our normal. So normal will be coming as m A2 divided by sin alpha and from this equation we can find out our normal is equal to mg cos alpha minus let me write it here. We already know value of A1, so we substitute the value of A1. This is 1, 2 and 3. Okay, using equation 3 and 1. So we take the value of A1 and substitute in equation 1. Okay, so we get this as mg cos alpha minus n is equal to m A2 sin alpha. From here we can find out our normal. We can say that our normal is equal to mg cos alpha minus ma2 sin alpha, and we already know our normal is given as ma2 sin alpha. We substitute here. Okay, so we can write m a2 sin alpha is equal to mg cos alpha minus ma2 sin alpha. You can also do it like this. Let the equation number 4. Okay, you can put it here using equation 4. We get ma2 sin alpha mg cos this. Now taking a2 altogether in one side, and also we can take it directly as common. We can write a2 m sin alpha plus m sin alpha is equal to mg cos alpha. From here we can simply find out our A2. A2 will be equal to mg cos alpha divided by m sin alpha plus small m sin alpha. So this is our A2 acceleration, and we can find A1 by using equation 3. Okay, we can say that using equation 3, A1, we put simply A2 as mg cos alpha divided by m sin alpha plus small m sin alpha into A2, that is sin alpha. This is our acceleration of the rod, and this is our acceleration of the wedge. Okay, this is acceleration of wedge, and this is our acceleration of rod. So simply we used equation 3, which is A1 is equal to A2 sin alpha, and we put value of A2 here, we get value of A1 as directly as, write it here, A1 is equal to this, and this acceleration of rod and acceleration of wedge. Thank you.